Hi, my name is Yuka Tashiro from Tokyo Institute of Technology. I will introduce the paper MR Microsurgical Suture Training System with Level-Appropriate Support. Advanced technologies such as artificial intelligence and extended reality are actively used in medical fields to enhance the capability of medical professionals. In training, XR has been used for more realistic training. In training surgeons, it is also important that training be simple. For systems to be accepted in specialized environments such as a medical field, it is essential to undertake design and implementation that takes into account the domain's expertise. For example, gauge surgeons are used in microsurgical suture training, one of the neurosurgeon's difficult techniques. The gauge suture training has been accepted in the field because it is simple and can be quickly interrupted and resumed. Despite its necessary, gauge sutures require many times with daily training, and practice tends to be monotonous. Thus, we consider that gauge suture training could be made more efficient by incorporating AI and XR. AI and XR have been used for training. We consider that their use cases can be categorized into three types: support for diagnosis, support for surgery, and support to enhance skills. In our research, we seek to support surgeons in enhancing their skills. As related research for the evaluation of microsurgical suture training skills, they proposed the system shown in the left figure. It is a system to objectively and quantitatively measure surgical skills by attaching markers to actual instruments. In the right related research, medical images are displayed by AR. Their researches succeeded in supporting enhancing skills, but the markers and sensors prevented them from capturing the detailed sensations in the fingers that come with using the actual instrument. Therefore, we propose an MR microsurgical suture training system incorporating different modes for skill levels based on the opinions of neurosurgeons and the gaze analysis. The requirements for the practical use of the system by neurosurgeons were redrawn as follows. MR system implementation. In the training routinely employed in the medical field, a video see-through head-mounted display is used since the utilization of MR, which allows the addition of information while minimizing the deviation from reality, is deemed optimal. It prevents neurosurgeons from being overly immersed in their training and does not disrupt their tasks. The system uses deep learning to detect expert focus points in microscope images. This enables markerless detection. Feedback is generated from detected values and displayed superimposed on the real time. Second, training mode by level. The technique of microscope suturing cannot be acquired in a day. It requires the adjustment of learning objectives according to the level of the learner. Therefore, two levels, the novice mode and intermediate mode, are designed and implemented. We developed a shadow matching system to help novices learn the position and orientation of surgical tools. We also developed a real-time visual feedback system to assist intermediate neurosurgeons in developing precise suturing skills. The flow of our research is shown in this figure. First, we move on to the explanation of the preliminary study. We received the following comments and suggestions from neurosurgeons who tried the system. Here are the comments from them. First, the gaze is a key factor to measure skills. Therefore, we collect and analyze the gaze data. Second, depth information is important. Therefore, our system uses a video see-through head-mounted display for looking directly into the microscope. Third, the visual feedback should not be always displayed. Therefore, feedback visualization changed from phase to phase. Based on the feedback of neurosurgeons, we developed a training system prototype utilizing an MR headset and recording gaze data from both novices and intermediate users. We find the following from the two results. First, novices have a more varied gaze than intermediates. Second, intermediates shift their gaze away from the tweezers when they move away from the knot point. Preliminary gaze analysis revealed that novices tend to gaze at surgical instruments, such as needles and tweezers, during suturing, more than intermediates. This suggests that intermediates have acquired a sense of ownership of tweezers in an environment with high sensitivity of movement under microscope, in terms of how to move the hand holding the tweezers and where to move it. Next, we move on to the explanation of MR Microsurgical Suture system. Based on the opinions of neurosurgeons and the gaze analysis, we designed an MR Microsurgical Suture training system incorporating different modes for skill levels. This figure shows the overview of the basic function. The system provides users with real-time feedback by connecting a microscope camera and an head-mounted display via PC, which tracks the position of the instrument and processes the image for the head-mounted display. To be specific, PC for detection uses deep learning to detect instruments and optical flow to detect the motion of the gauze from images received from the microscope camera. PC for display and scope calculates similarity and generates real-time feedback to be displayed on the head-mounted display. We use Vario XR3, a video see-through head-mounted display, to provide appropriate parallax. In addition, as the user head moves, the microscope image moves with it, bringing the view closer to the actual stereoscopic view of the microscope. The MR configuration enables training in an environment similar to that of actual suture training using actual instruments. In the case of VR configuration, training cannot be halted in the progress of training due to over-immersion. But in the MR configuration, training can be performed while viewing the surrounding environment. Next, we move on to the explanation of the novice mode implementation. We propose shadow matching for novices. In shadow matching, the system displays a shadow semi-transparent image of the ideal instrument's posture. The users train in handling the instrument by matching them to the shadows. This figure shows the flow of shadow matching mode. Our system divides into segments and mask instruments using YOLO V8. The system also calculates similarity between the ideal posture of instruments and the posture of the user's instruments. Next, we move on to the explanation of intermediate mode implementation. Feedback changes phase to phase based on the surgeon's opinion. Also, speech recognition is used to change phases. As shown in this video, when a user says loop,
Phase 3.
tweezer's motion circle and gauze motion warning will appear. The motion of the gauze and instruments is detected from the microscope camera image using deep learning and optical flow. Based on the detection results, a suture area circle and a warning message for gauze motion is displayed during the loop phase. The color and transparency of the suture circle changes depending on the position of the tweezers. The warning message for gauze motion is displayed darker as the gauze moves more roughly. After each suture, a scoreboard is displayed as shown on the right. Next, we move on to the explanation of the novice mode experiment. We conducted an experiment to measure the effectiveness of the novice system. 14 people with no medical background participated. Shadow matching and just practice conditions were performed in a between subjects experiment. The figure shows the result of similarity value using shift. The smaller the value of shift, the closer the image is to the ideal posture shadow. This result indicates that shadow matching tends to be able to practice without getting tired or losing concentration. This figure shows the result of UEQ. This result indicates that shadow matching is efficiency. Next, we move on to the explanation of the intermediate mode experiment. We conducted an experiment to measure the usefulness of the system for surgeons. 6 intermediate suture surgeons participated. With feedback and without feedback conditions were performed in a within-subjects experiment. This figure shows the result of the standard deviation of the tweezer's position. This result indicates that the real-time feedback is effective. The figure shows the result of a questionnaire on the role of each function. This result indicates that each feedback has a different role. Tweezer's motion circle was found to be useful for technical training, guard motion warning for technical training, and score for motivation. In addition, from subject observation, we found that a surgeon answered the phone while wearing the video see-through head-mounted display during the experiment. This suggests that the proposed system can be incorporated in the daily suture training of busy neurosurgeons. Therefore, this system could be considered to have accomplished one of the surgeon's requirements. At the conclusion, we propose an MR microsurgical suture training system with level-appropriate support based on the opinions of neurosurgeons and a preliminary study of gaze. Thank you for listening.